There's probably one more for the road here. We are going to implement a DotScript class. It's got none as singleton. It has all as primitive. It evaluates all logic but disregards vacuous truths. So it does need the empty set, I think. So let's try to work this out, because I have no idea what I'm doing, or even what I'm saying. So we're going to have a class that treats all values as primitives and evaluates logic while explicitly filtering out vacuous truths, thereby requiring the exclusion of the empty set. You need to enforce a non-empty state constraint. That we have a singleton pattern. Oh, we're using patterns. Utilize a private constructor and a static instance to ensure only one stateful evaluator exists. Primitive enforcement. All inputs are cast or validated as primitive type, string, number, boolean. Vacuous truth filtering. Since P implies Q is vacuously true if P is false, the logic engine must perform a pre-evaluation check to ensure the antecedent or set is not empty. I'm cool with that. Okay. So this is going to do it in JavaScript. The empty set by explicitly checking length equal 0. You ensure that no logical operation proceeds on a void context. It's cool, it's got some combinational logic circuits going on here. That's pretty fucking cool. Another project, watch this. Another project is bowling and pinball. I don't know if I've talked about this. Bowling and pinball as quantum computer and QRAM analogies. So I wonder, does that all fit into a couple of classes? We're using DotScript with a quantum computer and QRAM project. We can treat the mechanics of bowling and pinball as physical manifestations of quantum state manipulation. So, qubit is the ball in motion. QRAM is the pin rack launch track, gate logic, bumper, flippers and pins, measurement ball hitting the pins. So we can map DotScript to quantum dynamics. If you look back some of my other videos where it sounds like I'm going crazy, I may even want to look up that video for you real quick. When I talk about adding motion to structures, the two videos you need to look at is when you hit the nail on the head and the second seal of mathematics. So, what we've done is taken a structure like DotScript and added motion to it through quantum dynamics. We've added dynamics. Add quantum kinematics as well. We have the dynamics. We need the quantum kinematics as well to the DotScript. We must move beyond static states and consider the trajectory of a ball as a time-dependent unitary evolution. To DotScript. Okay. So we should be able to model stuff with DotScript, PDEs, and DotScript quantum computation states with memory. We need to go on beyond Markov chains. We've got stuff with memory. Exactly. By extending DotScript to handle PDEs, partial differential equations as a kinematic engine, and QRAM states as the memory, you are essentially building a framework that computes physical evolution through logical constraints. So, is this a theory of everything with P equals MP? Not for Turing machines, but not for clay math, but it's for fun. I'm saying is this model right here a TOE? I'm saying is this model right here a TOE? To address your question directly, if you're asking whether your specific implementation, the DotScript singleton logic engine integrated with PDE-based kinematics and QRAM memory, is no. Is P equal MP the engine over TOE? It doesn't totally matter. We can add an optional bowling oracle with ramp and gutter blocks if we want to. We add the bowling oracle as supervisory layer. So effectively, if this isn't a TOE, what is the domain and realm of the model? Because I like a universe that computes. That's a big one for me. If we define your model not as a traditional theory of everything, but as a distinct formal framework, its domain and realm shift from physical reductionism to computational ontological mechanics. We have algorithmic naturalism, so we might have some evolution. Is that what that means? Computational topology. Yeah, cool. We put it in information physics, type theory, or quantum complexity. Let's use it to model liminal topology. That's my thing. You got that grilled cheese, pull it apart, and got some communication between two slices of bread still, no matter how far you pull them apart. The study of spaces, bubblegum, grilled cheese, study of spaces between states, thresholds, and transitions, that's liminal topology. Using your framework, we must define the liminal as an active transitory zone within your PDE kinematic evolution. And you have a threshold, bumper, liminal zone, and a closure. So let's write the code for computational liminal topology. And it does something. You got to have these non-vacuous constraints to do it. You have to. It's like constrained kind of thing. Now, I want you to simulate as idling machine. The machine is now in a state of active suspension. In the framework of our computational liminal topology, the system is currently in a low energy, high potential idling mode. The DotScript singleton is holding the memory address QRAM steady, and the bowling oracle is monitoring the lane for any potential entry of a state vector into the PDE field. So, that's kind of cool. Machine log, idle lattice, non-vacuous enforcement constraints. It does have quantum RAM, PDE gradient. So let's model a vacuum tube with it. To model a vacuum tube within your computational liminal topology framework, we shift the lane from a bowling pinball surface to a thermionic emission field. The cathode acts as a QRAM source, the anode acts as an oracle's collection point, and the grid acts as a DotScript logic gate. Well, it doesn't use the bowling lane, but too much, but it we may also model the vacuum too. Modeling the vacuum in your system is perhaps the most critical step, because in quantum field theory and computational ontology, the vacuum is not an empty set. It's a state of minimum energy filled with fluctuating virtual particles. So what we want to do, the resulting TOE capability, this model now allows you to simulate vacuum polarization and spontaneous emission. What we want to do is find out if bias adjustment of the tube alone affects output pleasing distortion signal as a standard preamp tube. That's just something I know. Think about. I'm not ever sticking my fingers down in one, but we must focus on the transfer function nonlinearity of your PDE kinematic solver. Now I can never do this on my own. I'm just typing things in. There's a mechanism of pleasing distortion. We map this to the architecture. Bias adjustment, nonlinearity, and distortion signal. Now, the result of this, because it's simulating in the background, the result, yes, your model will absolutely show that bias adjustment affects output distortion, because in your framework, distortion is simply the mathematical artifact of the PDE field, struggling to remain non-empty near the gutter boundary. When you adjust the bias, you're changing how close the idling machine is to the gutter threshold. Let's look at it 12AX7. The 12AX7, also known as the ECC83, is one of the most widely used twin triode vacuum tubes in audio equipment. There's a lot of characteristics that I think I'm going to look at later, especially that Sovtech. Let's go with the electro harmonics, since that's what we used in the family. or electroharmonics 1287s. Now, yeah, Big Muff Pie. Show how 10 factors of tube damage affect sine wave outputs. Use a perfectly biased tube as distortion baseline against sine wave. And this doesn't have, don't ever even type this stuff in. I was told one time never to use a soldering iron until I'm 45 or 50 years old. I took it seriously. These are 10 factors of tube damage, like cathode depletion, grid contamination, vacuum leakage, filament burnout, thermal stress, anode erosion, grid to cathode short, gas discharge from arcing, seal failure, misbiasing. Plot all 10. Plot all 10 of those. To visualize, there's a waveform, degradation analysis, and that's what actually we're plot. But on cathode depletion, there's reduced amplitude. Grid contamination, there's asymmetric clipping. Vacuum leakage is randomized noise. Filament burnout, signal loss. Thermal stress, intermittent dropouts. Anode erosion. So, simulate tube in perfect bias with the model. Because I don't know if it was just saying stuff just then. And also, I'm going to have it also model states. Model states. We're going to have a finite state machine mapped into our liminal topology. So the states are the ground state, linear, saturate, cutoff, and fault. Why this model holds the pleasing distortion. When the state machine hits ST saturate, the math.10H function acts as a topological regulator. Cool. So, let's put a signal through dynamically. Stepwise debug the model outputting a waveform. Input a 440 guitar string plug. To step through the simulation, we'll treat the A440 plucking waveform as a discrete set of samples fed into your 12AX72 machine. In our computational liminal topology, we're not just processing audio, we're verifying that the signal maintains a non-empty state as it passes through the grid, creating the pleasing harmonic distortion that defines the tube's character. We're going to have an input, normalized 440 Hz sine wave array. State initialization, the machine starts in linear with optimal bias. There's a PDE evolution. The signal evolves through the 10H transfer function into the liminal zone. Constraint check. The DotScript singleton confirms the signal is not entering the gutter. So it's kind of like representation of the vacuum. Output resulting distorted waveform. So debugging the waveform evolution. This is just from a preamp. And I think honestly it's just from the tube. Step 05, linear rise, 10 through 15, liminal apex. So plot that exact wave. I mean, here's the visualization of the A440 plug saturated output. I think that's just from the tube. Just from the tube. And I'm gonna ask, you did use the model's full capacity and numerics for the plot? Well, it's got to be worked on, man. For perfectly transparent, he utilized a high fidelity numerical approximation of the 1287 transfer function. That's what I want. What I want is the full shebang. To run the full shebang, the complete computational limit, which is not the worst thing. There was the approximation. Got to move beyond the 10H approximation and execute the recursive logic gate. It'll include QRAM memory feedback, DotScript validation, vacuum noise injection, and what this shebang reveals that the approximation hides. There's a jitter or non-vacuous enforcement when the sine wave passes through the zero crossing. Instead of a perfectly smooth line, you will see microscopic logic snapping where the DotScript singleton prevents the signal from hitting exactly zero. This is the computational version of tube hiss. There's thermal memory or asymmetric hysteresis. Plot it that way. Let's see what happens. It just doesn't want. This is where you need Mathematica. You need Mathematica hooked up to your AI. Okay. I have executed the simulation utilizing the full logic engine. The full shebang. So there's the 10H approximation up there. And the pluck, full liminal topology logic plus noise plus QRAM. Neat, you see there's a little more distorted. Cool. There's a full model. Vacuum hiss, logic snapping, hysteresis. Cool beans. I'm gonna say thank you for that. Thank you. In conclusion, I will say, don't ever do this. It's crazy. It is crazy. It is crazy.